Hello, math fans. Thanks for sticking with me, if anyone still is, through these cribbage videos. This mostly has been an opportunity for you to see me try to struggle through proving something. I think I've proven something maybe that hasn't been proven before. I mentioned in the last video that I just don't think very many people would have asked this question. But taking what I did in the previous video and thinking about it, I realized, hey, that works. We were trying to add up to the number 15. Because in cribbage, that's what you're trying to get. Using the fact that 10s, jacks, queens, and kings are worth 10, aces are worth 1, and you can do any sort of combination just to get 15. And we found it was around 17,000. We proved that. That was part of the story, but I said there's nothing really special about 15. I could pick other numbers once I have this general approach. So I'm going to talk about the approach again, recap, and then talk you how, in thinking about it over a few days, I realized some better things I could have done. I'm sure there's even better things I could have done along the way, but the method I used wasn't specific to 15. And so I basically prove it for all of them. Every possible sum I found, and I found every possible number of ways you can do it. So here's a random one that happened to have a whole number. There's 100 ways to get 335 from a 52 card deck using cribbage rules. Don't ask me to list the 100 ways. Probably could figure it out, but anyways. But a recap of the idea I had, and this wasn't my idea, it's just something I remembered from a combinatorics class in grad school about counting. And this idea was to think in terms of polynomials. They actually do a pretty good job of encoding something that otherwise would be hard. So I talked about how aces, I could think of the aces as these exponents. 1 ace, 2 aces, 3 aces, 4 aces. And it's a the course where I studied this, we were studying infinite series and generating functions. I absolutely love the course. So I'm so happy that I got to come back to this. It resonated with me, some of those methods, and I just haven't really used it. I'm not a practicing mathematical researcher. I just teach tons of students all the time. I was a good student. I was a good researcher at one point. I've just gotten too busy with teaching, and so this is giving me a chance to go back and visit some things. Maybe this is interesting enough that I'll ask some of the people in our department. I just don't really have time to publish things, but maybe there's something here. I'll report again. I guess there might be one more video if there's more to be done. But I mentioned that I then added, I included a 4 here because there were 4 ways you could have 1 ace. There were 6 ways you could have 2 aces. There were 4 ways you could have 3 aces, and I've done that in the previous videos. And then I said, what happens if you multiply this by the possible 2s? So you can have 1 2, you can have 2 2s, which is 4, you can have 3 2s, which is 6. And if you've never seen this before, it's really bizarre, but it shows you this very different use of polynomials. We're basically using the polynomial as like a clothesline. That's what one of my professors used to say, to hang these numbers. And we're actually studying the exponents, because if you multiply these two things together, you're going to get x to the 9th. But that 9th will really be 6 plus 3. And you can say, well, there's 4 ways we could have gotten the 3 and 4 ways we could have gotten the 6. And so the number in front of that 9 is going to be a 16. In addition, if there's any other 9s, they'll be included. But this counts the number of ways in a clever way. So I did that in a previous video. And I talked about this when I first was thinking about these ideas. And I even did some examples. I said, here's all the ways up to 3. And I multiplied this. So watch that previous video on that. And it matched up. And the number in front of x to the 15th was 320. It was great. All was great. At the time, thinking back, I should have realized that this looks really familiar. This is part of the so-called Pascal's triangle. If you've never seen it before, then maybe that's another video. But that means this is an expansion. It took me many days to see this because I was doing other things and I was like, hold on, why am I not saying that this is one? I feel bad to admit that I did not see this for a couple days, that is that. And this one's the same thing, but with an x squared plugged in. And I was like, oh, this is much easier to write. Why was I writing it that hard way? Again, I'm out of practice. Haven't had time to do research for 20 years. So I started to do this and say, hey, that's the same thing as that. And so then before I got to the tens, because I knew the tens were kind of a different challenge because there were more tens because of the tens yet, I stopped at 9. So after the long drive home from Thanksgiving, I'd been thinking about this. I stopped at 9. I plugged it into Wolfram Alpha, and it was able to handle that. Just barely. And this is the expansion it gave me. And so then I wanted to do some testing. I said, how many ways can I get a 2 using only 1 through 9? And I was like, well, you could have 2 aces, 1 plus 1. And there's 6 ways to do that. And you can have 1, 2. And there's 4 ways that it should be a 10. And then I scrolled down and I was like, yay, it's a 10. And then I just wanted to check one more. I've learned through errors many times and being too excited about a result too early to do many experiments. And this I still probably haven't done enough, but enough that I'm pretty convinced that there's something interesting here, even if what I have, I'm pretty sure we have it here. Anyways, so then there's 601 ways to get 8. So that took me a little longer. I penciled out what is every way I can get an 8. And I got 601, and then I went down and looked, and I was like, all right, I'm in business. So then I included the tens. Now the tens, there's a lot of ways to do it because you can have 10, Jack, Queen, King, and there's 4 of these and 4 of these and 4 of these. But in all respects, those are equivalent. So it's like there are 16 tens. So then I started to go, okay, you can have 10, you can have 2 tens, you can have 3 tens, you can have 16 tens, which should have 160. You can have 15 tens, 150. But how many ways? I was like, oh, it's the exact same thing because you're going to choose 1 from the 16, and then you're going to choose. And this, I didn't say this. This is 4, choose 2. This is 4, choose 1. And so this is also part of the Pascal's triangle. 16, choose 3. How many ways can you choose 3 of those? And so forth. This would be 15, 16, choose 15. And that means this whole long mess is 1 plus x to the 10th to the 16. Now, Wolfram Alpha would not take that. It was too big. So I had to remember how to log into Mathematica on my work computer, which I hadn't done for probably 10 years. So that took a little bit of time. But eventually, I was able to use the full Mathematica and do a full expansion. Mathematica can handle big things like this in a few seconds. So I expanded this out, and this is the terrible thing I got. Now, if I were going to publish a paper on this, I would just sort this information into a table, extract these numbers. And if you really want to be a true secretive mathematician, you then don't tell anyone how you got it. But anyways, here's the number, the 15, the coefficient, the 17,264, which I've been talking about for the last couple of videos. But the point is, that's just one of the numbers. I was like, what I did will work for any of these. So I know how many ways you can get 78. This many ways. 113 billion ways. I know how many ways you can get, 224. This many ways. 8 trillion ways. 8,263,000,000 ways. I thought that was pretty remarkable. Feels like one of the best results I've ever proved. Probably not that interesting, but I'm easily amused now. So anyways, the result I put at the beginning, I was looking for a whole number. There's a symmetry to these. 340 is the biggest number you can get. That's it. I should check that. That's if you used all your tens. If you use all your tens, that's going to be 160. And then you add up all the other numbers. If you want to know how to add up the numbers from 1 to 9, then you got to watch my video on Hippos Go Berserk. 9 times 10 over 2. And there are, if you add up all of those, there are 4 of those. So 4 times this. So let me just do a double check. I should have done this ahead of time. But that's going to be 2 times 90, so 180. That's what those add up to. And then my tens, am I right to say 160? I'm doubting myself now. I should have checked this ahead of time. Because we have 16 of them, each of them are worth 10. Oh, and those two add up to 340. I was thinking that 180 and the 160 didn't add up to 340. Phew! All right, good. So anyways, here's the 335. There's 100 ways to do it. There's 601 ways to make 332. I know those numbers are probably too small. If someone needs to know how many ways to use cribbage rules to get the number 150, you can send me a message. And I will tell you, I don't know how I'm going to publish this number, but I'll tell you it's about 51. Let's see, that's thousands, millions, billions, 51 trillion ways. But I think that's pretty awesome that we have all the results there. I think this was a pretty good journey through counting. Well, in cribbage, counting cribbage, you might say, who cares about this? But being able to count things in a formalized way and answer so many questions at once, that is pretty valuable. If anything, just for your gameplay. So please ask me about other games. Go back to my first video. Give me comments. I'd love to do some of these same analysis. All right, I think I've squeezed as much as I want to out of cribbage for now. Again, this entire series is dedicated to my aunt, uncle, and cousin, Rick, Sharon, and Gail. They have played cribbage. It's been a big part of their lives, and I'm kind of late to the party, but I've been teaching my son, and these are some of the questions we've had. All right, thanks for listening.